Hello. Today in Geological Activity Explained, I'm going to discuss why are most earthquakes very small and therefore not dangerous, and only a few ones very large and often extremely dangerous. Large earthquakes can have devastating effects. One such effect is seen here, and that was a tsunami generated by an M9.1, so very large earthquake, in Japan in 2011. Some 18,000 people died. The destruction was enormous, and hundreds of thousands lost their homes. Tsunamis, or so-called harbor waves, are very long ocean waves, and they are generated by sudden displacement of seawater. It doesn't have to be displacement due to earthquakes. For example, landslides or eruptions on the seafloor can generate such waves. But large earthquakes are very common reason, and then the wave is due to a sudden displacement, sudden fault movement. And here we see such a case from a magnitude 9.2 earthquake in 1964 in Alaska, and we see how the wave was spreading through the ocean from its origin here at a subduction zone. This was a thrust fault, that means a low angle reverse fault. I'll explain that in a moment. But we see here in hours how the wave was spreading out from its source, from its origin. Now, all tectonic earthquakes are generated by slip-on faults. So they're indicated here by these arrows. This is the old classification from E.M. Anderson many decades ago. So they are basically shear fractures. They're driven by so-called shear stresses parallel with the fault planes. And the basic classes are normal here, strike slip here, and reverse here. Now, in the case, the dip of the angle of this fault with reference to the horizontal plane is less than 45 degrees, as was the case in Alaska in 1964. We call it a thrust fault, and these are the most dangerous ones. These are the most dangerous ones. I show here also the stress field, but that's not so very important for us now. We see this perhaps better now, particularly the thrust fault. You see here, this of course is a normal one. This is a reverse, so it's relatively steeply dipping, as you see. This side goes up, that one goes down, and then we have a strike slip fault. And the thrust one, seen here, is so that the angle here, this angle here from the horizontal plane and down here to the fault plane, is less than 45 degrees and often much less than that. And unfortunately, as I say, thrust faults in subduction zones are the most dangerous earthquakes and lead to the greatest death toll. Here's another example of a thrust fault again. This one was in 2004 in Sumatra, so here. And again, this map shows the spreading in hours of the tsunami, of the oceanic wave, that when it comes on land, first to India here, comes on the coastal area, then it magnifies and becomes very, very tall wave that can devastate everything in its path. In this case, it was generated by an earthquake that was rupturing up to 1,600 kilometers, so horizontally, and with a slip of around 15 meters. The death toll is estimated to have reached 228,000 people. Now, as I say, earthquakes are the most devastating, the most deadly, frequently occurring natural hazards. Again, here in 2010, in Haiti, there was an earthquake at around 13 kilometers depth, 25 kilometers from the capital. It was not very large, magnitude 7, and it was a displacement of on average of 1.8 meters, partly thrust and partly a sinister strike slip fault. So it was a major earthquake, but not a great one in the classification I'll show you in a moment. Yet the destruction was enormous, enormous. And it resulted in one of the largest recorded death tolls ever of earthquakes. The estimates range from 100,000 to 316,000, but definitely the death toll was enormous. Here we see the totally collapsed cathedral of the capital. So a list of the deadliest earthquakes since 1900 shows that in many large earthquakes, the death toll is over 100,000, can be several 100,000 people. And again, I emphasize, of frequently occurring natural hazards, the death toll is by far the largest in large earthquakes. Of course, these are all estimates, and some figures may be slightly disputed, but it doesn't change the fact that hundreds of thousands of people can die in large earthquakes. So what is an earthquake? Well, what does the name tell us? Obviously, it is ground shaking. For a tectonic earthquake, the ground shaking must be due to slip movement on a fault. Here we see one fault. The part we see here is around 11 kilometers long. This is in the rift zone of southwest Iceland. I've often showed you. This one is called Hrafnagja or Raven Fracture. It's a normal fault. Those do not give rise to the largest earthquakes, definitely. It's a lake here, the Lake Thingvallavatn. And if I take a section here in our imagination through the middle of the fault, roughly, and what would we then see? I will show it on the next slide, but remind you, in a displacement on a fault like that, this wall would subside and this would rise a little bit. So the uplift is much less than the subsidence. But there is displacement both of this wall and that wall. So let's look now at the imaginary cross-section through here. It might look like that. So this is a vertical cross-section. We see the total fault here, so half of it in fact, because I'm in the center. And we have several concepts here. One is the strike dimension. So strike dimension is the total length at the surface of the fault zone or the fault. Now, during most earthquakes, nearly all earthquakes, only a part of the fault zone or the fault is slipping. And then we speak about the rupture length. That part that ruptures during a particular earthquake is the rupture length. That part that slips or moves during a particular earthquake is called the slip. But then, of course, because earthquakes occur frequently in the same fault zone, there is a cumulative displacement, this one here, which is usually much, much larger than the slip in individual earthquakes. And we call this the strike dimension, and this, the vertical one, the dip dimension. In earthquake mechanics, they call this the width. But in structural geology tectonics, we usually call this the dip dimension and this the strike dimension. So we have the total strike dimension is the total length of the fault zone, whereas in individual earthquakes, we have a rupture length. That is the part of the fault zone that was moving during the particular earthquake. And similarly, we have dip dimension, and along the dip dimension is a displacement, a cumulative movement of all the earthquakes that have occurred on the fault. But individual earthquakes, when we talk about that, we call it slip. We call it slip. Here I show a curved normal fault. I don't know if the Raven fracture Armenia I showed you is a curved one. They're very common in sedimentary rocks, like in sedimentary basins, but they may also be in a lava pile that we just looked at. So even in large transform faults, such as the famous San Andreas in the United States that we see here, and the North Anatolian fault in Turkey that we see here, they are with more or less continuous seismicity, but mostly very, very small. In fact, most of the earthquakes that occur on these kind of faults are not felt by humans. If the magnitude is less than around 2, people don't feel it, usually. So let's now look at some statistical data on how many small earthquakes versus large earthquakes occur in general. Here is a summary of it. And if you look at this data here, and you see the names given to, so great earthquakes is 8 and greater in magnitude, major earthquakes are 7 to 7.9, and then we have strong and so on and so forth. But if you look at this data set from 1900 to 1919, there are obviously millions of earthquakes per year that are of minor or very minor magnitudes. And I show only here down to magnitude 1, but there are many earthquakes that are magnitude 0 or even negative magnitudes. And these, of course, are not felt. As I said, earthquakes less than 2 are not felt by humans normally. There's another thing about the magnitudes, because these are logarithmic scales. A change in magnitude by 1 unit from say, magnitude 6 to 7, then the released radiated or seismic waves energy increases by a factor around 32. By a factor around 32. So an earthquake of magnitude 8, a great one, radiates million times as much energy as an M4. So it's very important to keep in mind one great earthquake releases more energy than millions of minor or very minor earthquakes. And the radiated energy is, of course, a measure of the earthquake's potential to damage or even destroy completely human constructions, and therefore, of course, damage and destroy human lives. Now, earthquakes follow so-called Gutenberg-Richter's frequency magnitude law. This is a power law. Power law is one of very many laws, statistical laws, where there's a lot of small things or processes or events and very few large ones. So here we see worldwide earthquakes from 1904 to 1980. And if n is the cumulative number, that means a number larger than a given magnitude m, then we get this kind of relationship here, where log is for the logarithm to base 10. Now, if you were getting rusty about logarithms, just remember they were initially invented to make calculation of large number easier, and a logarithm is basically a power. It's a power, say 2 in the power of 3, and so on. The power is a logarithm. Here, the b value is the slope of the line on the log plot here, and the a value is the intersection with the horizontal axis. Now, if b is high, is this steeply sloping, then small earthquakes are very common. And in non-volcanic areas, B is commonly 0.8 to 1.1. But in volcanic areas where you have very many small earthquakes, you have B up to maybe 2. Now, to understand better why most earthquakes are small, let us look at one of the best exposed transform faults in the world, namely the Húsavík-Flatey fault in North Iceland. This is a 90-kilometer long fault. It's a dextral fault. That means that the movement, when we stand here and look across the fault, the movement is here to the right. It connects a mid-ocean ridge here called Kolbeinsey Ridge and the rift zone in northern Iceland. And the rift zone in northern Iceland is a surface expression of a mid-ocean ridge in a way. So it's 90-kilometer long here. It has a continuous seismicity. All these little gray dots are a seismicity, are earthquakes. Each dot is an earthquake over a certain period of time here. And it can generate once every few centuries, perhaps, magnitude 7.1, 7.2, something like that. And I will show you now the situation here where part of this fault, the less active part, is exposed on land, but at depth of 1.5 kilometers, namely 1,500 meters below the original surface of the lava pile. So this has been eroded here, so we can see into the fault and see what kind of structure it has. So I will show you here in the next slides. I will show you this area here, these cliff sections here on the coast. No one is living there anymore. People, of course, living here. There's a town here called Húsavík, and then town here, Dalvík and Akureyri, so on. But there's no one living here on this coastal area anymore. So earthquakes are very frequent there, and I'll show you what the internal structure of a major transform fault looks like. So this is a classical structure of any fault zone, but here I show it for a right lateral or dextral strike slip fault, just like the Húsavík-Flatey fault. So the movement here is to the right, and every fault zone of this kind has a central part that we call the core. The core is composed of crushed rocks. It can be clay, but in general it's breccia, with, as I say, with some clay, breccia, broken up rocks. It is much thinner than the thick damage zone on either side. And the damage zone is characterized by fractures. And the fracture frequency, the number of fractures per unit length, is highest here at the contact, and then decreases irregularly with distance from the contact. And then we go into the rocks around it. So the whole fault zone is the core plus the damage zone. In gigantic fault zones, in fact, you may have more than one core, and the damage zone can be divided based on number of fractures into several subzones. So let's look at this one here in Iceland in the Húsavík-Flatey fault. Here you see a core. This is completely crushed rock, around 10 meters thick. You see a person here for scale, it's a rather small person, in fact, but this is around 10 meters thick core. Another thing you notice, this is the damage zone, part of the damage zone. This is part of the damage zone, and that's a part of the damage zone. The damage zone in this area is, in fact, up to several kilometers in thickness. And what happens in the damage zone? Well, first of all, there's a lot of fracturing, as I'll show you in a moment. But in addition, the lavas, these are lava flows, initially basaltic lava flows, they have been tilted, rotated. So they dip now, they're inclined now 40 degrees, whereas initially they were horizontal. So this is due to the deformation related to the seismicity, to the fault movement. If you look at other transform faults, like the San Andreas and the North Anatolian faults I showed you earlier, yes, The damage zones there, the estimates vary a little bit. They can at least up to hundreds of meters and occasionally up to a few kilometers. And the cores may be up to many meters. So we're seeing something similar to what we see here in the Husavik flat fault. In all cases, both the thickness of the core and the thickness of the damage zone vary along the strike dimension, and as well with depth. They vary with the depth. So here is a part of the damage zone of the Husavik flat fault. And we see that, of course, as expected, there are numerous fractures. We are here making a study of this damage zone. So we have a measuring tape here. This lady is here for a scale. And we see that a lot of these fractures are filled with secondary minerals. They're so-called mineral veins with calcite or quartz and zeolites and so on. So many earthquakes in fault zones, big fault zones, are generated when these kind of fractures propagate themselves. They themselves are not necessarily, or in fact, the minority of them are faults, shear fractures themselves. They're extension fracture, fluid-driven extension fracture, but in their walls and at their tips, they generate earthquakes, very, very tiny earthquakes, numerous, very small earthquakes. So let's look closer at this one here. So yes, we see there is displacement here. There is displacement here. And here, of course, there are many small displacements, but most of these veins themselves are extension fractures. They're formed by the fluid pressures. The fluid pressure is an old geothermal field, and the fluid pressure breaks the rock. The fluid pressure breaks the rock. You see here for scale, my measuring tape, Stanley measuring tape. But when the fluid pressure goes in here, it generates stresses in the walls, and these stresses can generate tiny little slips and tiny little earthquakes. In addition, transform faults like this one here, many of them have dikes. Many of them have dikes. So magma-driven fractures that again generate earthquakes when they're propagating by causing stresses in their walls and at their tips. So here we take an example. Let's say a dike is propagating here, and it gives rise to pressure propagating through a lava flow with a lot of cooling or columnar joints. So when the dike is propagating, its pressure translates into stress, and therefore there will be a lot of tiny displacement on the already existing cooling joints, columnar joints in the lava. And because the fractures, the cooling joints themselves are very small, the displacements are bound to be very small, and therefore the earthquakes generated are bound to be very, very small indeed. So this is very common. This is very common. In addition, this loading doesn't have to be due to dike. It can be due to the loading of the fault zone itself. But in any case, the movement, the displacement, are limited by the size of the existing fractures, which is very low, very small, and therefore the earthquakes will be very small. In addition, as I say, at the tip of a propagating fracture, whether it's a dike, a mineral vein, or a fault, there is a process zone where there's a lot of microcracking. And microcracking gives also rise to earthquakes, tiny ones usually. And then gradually this process zone becomes a part of what we saw earlier, the damage zone and the core of the fault zone. Now, how does this all relate? Well, the energy released by an earthquake is partly due to or through work, movement of the faults, of the fault walls, heat due to the friction along the fault, and part is radiated as seismic energy, giving these waves that we are talking about here and used to measure the magnitude. But the main point here is that the area, the red one here, that slips during a particular earthquake. And the size of the slip, and these are in fact related. So the area here, A, the size of the slip, delta U, multiplied by the so-called shear modulus, an elastic constant or modulus, they give what is called the moment. The moment, which, as I say, is a measure of the energy released in the earthquake or the slip. And this moment is directly related to the moment magnitude, which is the most common earthquake magnitude scale today. So the older scales were the Richter scale, the local scale, and the surface wave scale and body wave scales, but the moment scale is probably the most commonly used today. So these are directly related. So if we have a moment here, we can use it to correlate with the moment magnitude. So the smaller the area here, the smaller will be the moment, and the smaller will be the earthquake magnitude. Or conversely, the larger the area here, the larger the slip, the larger will be the moment and the moment magnitude. So here is an aerial view of a fault zone again. I've showed you similar photos before, but this one is taken from a distance, and it shows around 8 kilometer long part of the Armenia normal fault in the rift zone in southwest Iceland. There's a lava shield in the distance. And we see that this fault zone is continuous for nearly 8 kilometers, but it is composed of many fracture segments, many segments. But at the end, these segments gradate into, in fact, tension fractures that I will show you on the next slide, but then I look down to the southwest, and there are tension fractures here as well. But what it shows is that every big fault zone is composed of many smaller segments that in turn are composed of even smaller fractures. So there's a huge number of fractures that can potentially slip in each fault. So let me show you this on the next slide. So we look on the next slide, as I say, at this one here, a beautiful set of tension fractures, but then we looked in this direction down here to the southwest. So these are what we call echelon fractures. They are all parallel, but they're oblique to the underlying fracture. They're all tension fractures. They're not really faults. They're just pure opening. And this one here next to the white car, this one here measures 12 meters in opening. So these are big fractures, but they're still smaller than the larger segments of the Armenia. And as I say, this illustrates that when you go into a fault zone and you look at the fractures there, you find smaller and smaller fractures, meaning that each fault zone is not just a single line on a map as maybe sometimes drawn. It is composed of numerous fractures that range in scale down to very, very small fractures. So if we go into the field and we measure the fractures in a fault zone or in any fracture system, we find usually this kind of distribution. This is a cumulative distribution, means that the first bin or the first point here includes all the fractures. It's all the fractures larger than 0 or 0.1 meter here in this case. The next bin includes all fractures larger than 100 meters. The third bin, all fractures larger than 200 meters, and so on and so forth. So we get this kind of distribution. It's called a power law, but in fact, negative exponential laws can also be fitted to this kind of distribution. This is still not really understood well. It's very common distributions of various processes and items, both in nature and in human society. So people are looking very much into it. We can then plot this on a log scale, so-called bilogarithmic scale, where you have log here and log there, and then we can see if there's a change in the slope on these kind of graphs. That usually indicates a slight change in the mechanics. So often the shorter fractures here, maybe tension fractures, the longer ones are more commonly faults. But that's not the important point here. The important point here for us is that in any fracture system, any fault zone, most of the fractures are tiny and a few ones are very large. A few ones are very large, meaning slips on the tiny ones give rise to tiny earthquakes, small magnitude earthquakes. Slip on the few large ones gives rise to the big, the dangerous earthquakes. So repeating, every single fault zone, every single fracture system has large fractures, also comparatively large fractures or segments, but many, many more small ones. Many, many more small ones, which is a formal explanation why most earthquakes are tiny and only a few ones are very large and dangerous. Then you could ask, all right, but you basically just moved the problem because you haven't explained why. What is the mechanics? What's the physics behind most of the fractures being small and only a few ones comparatively large? Well, that is the job I intend to address or do in my next talk on Geological Activity Explained. So I plan there to explain to you from a stress point of view and fracture mechanics point of view why most fractures, tectonic fractures, tend to be small in any system or any fault zone, and only a few ones are large. But before we end, I would like to show you here how dangerous earthquakes really are, as we all in a way know. This earthquake here in Armenia was only magnitude 6.8, so it's not very large. It happened in 1988. It was a reverse fault seen here at the surface where the gentleman is standing. The displacement is here 1.6 meters. It is an extension of in fact, a reverse fault. But at the surface here, obviously, this is of a thrust fault, but obviously here at the surface, it's a reverse fault. So it's a strong earthquake, but not a major one. Yet, in this earthquake, tens of thousands of people died and hundreds of thousands were injured. So this emphasizes the great importance in science for human society that we can really advance our understanding of the geology and physics of earthquakes with a view of, we hope, being able to forecast in the future the large earthquakes. And with these words, I say simply, thank you very much indeed. And for now, bye-bye.